Appreciate it. Hey everyone, I'm happy to be here to talk to you about more about physical AI, AI in the physical world. There's quite a bit. I think most of you work on AI. I don't know how many of you work in the physical world. Show of hands. Not many. So I will. Then this talk should be very welcome. So much of my talk is about cars. Physical world is not just about cars, but this is going to be about self-driving quite a bit. So I bought the car a couple of months ago, and I drove to Cornwall, and it's about 5 hours. So 5 hours that way, 5 hours back, it's 10 hours. And it has a state-of-the-art drive assist system. And I think it helped me about 1.5 to 2 of those 10 hours. And for the rest, it just didn't apply. So now, in a world where AI is ubiquitous and it's everywhere, and maybe it helped me prepare the slides, maybe it helps me understand my email faster, and so on, how come this technology is not yet powering cars? But wait, it almost is. So I will talk to you about the technology that we're developing at Wayve. We are looking at developing self-driving technology that applies to many cars. I bought the car, right? So I went out there and I bought the car from a dealer. We are putting our technology in cars, in private cars that you'll be able to buy. So we have to work with many cars. We have to work with different sensor sets and so on. This is counter to where the industry is at now, where there's quite a bit of bespoke development for every car, for every sensor set. Our cars are learning from data. They're not programmed. So we're not programming. We're not saying this is a lane. You should drive on the left. You should drive on the right. We simply let the cars learn from a variety of data. That way, they adapt much faster to new environments. Because they were not programmed to drive in the previous environment, they will drive in multiple environments. This is what helps us get to a global scale from country to country very easily. So we have been at it for a few years now. And the physical world, unlike cognitive AI, requires you to actually make things move and then learn from that. And there's quite a bit of imperfection in the physical world. Two cars will have slightly differently inflated tires or steering bias and so on. And you need to go through all of that. And you need to develop your technology. You need to collect the data. How do you collect the data? You need to deploy at scale. And then you have to learn from it and iterate through this. And what's really important here is you need to develop a very good tool chain. This tool chain allows us to move faster. About a year ago, we reached an inflection point. A year ago, we were driving primarily in London. Now our cars drive across the world, Japan, Europe, UK, US. So what's the secret? Well, if you look at how self-driving and general robotic stacks have worked traditionally, it's the picture that you see at the top. There is some sensing, and then there are some intermediate representations that you work on. And these intermediate representations give some comfort of, I understand what the world is made of. For instance, one intermediate representation is a list of objects. The car sees a list of pedestrians and bicycles and so on, and it models them based on some predefined model. Pedestrian walks this way, a car behaves that way. We took a different approach. We said, rather than understanding what every object does, the car should learn to drive from example. Like, as a human, hey, if I drive in Shibuya, where we took the car in Japan, there are these crosswalks with thousands of people at a time. why would you really model 1,000 people? They're not in your way. They're not relevant to the driving task. Why would you spend compute in a 75-watt budget, super constrained, for something that you don't need to use? So here, we're letting the model figure out what it needs to pay attention to. And of course, we validate it. So this allows us to remove this intermediate state that otherwise would be a liability. The intermediate state needs to be not just tested, but when you go from place to place, let's say you solve driving in a small environment, but then you go to another environment and the rules change. If you try to manage the state programmatically, you're going to end up with a house of cards. It's very hard. It will work in one place, but it's very hard to expand. So in contrast, what we do is we have a network that we train, and then we run it everywhere. We have one model that runs across countries, across cars. So in a way, this is similar to how language learning has evolved. I happened to work on language understanding before neural nets started to work at scale. And it was a rule-based system, and there were many rules, and it was very fragile. And people worked on it for years, and it was a large investment. And then with large language model, language emerged, right? Like you can point it at Wikipedia, and it will learn various languages that you don't really intend to learn. So our driving is similar to that. Now, driving and learning and language are different tasks. But there is an emergence of it learns from one example and it carries to another example. So product-wise, I talked about driving. And driving as a product, driving assistance and self-driving, there are several layers. One of them is hands-off. And for hands-off driving is what could help one drive to Cornwall and back with quite a bit of assist. Like you basically don't need to touch the wheel, but you need to keep your eyes on the road. You're still responsible. Eyes-off driving is my favorite. So personally, I would like my 10 hours back, right? So with eyes off, I could have worked, or I could have done anything else, right? And so I used to commute. I spent much of my life in the Bay Area in the US, and my commute was long. It was about an hour and a half round trip. And if you think about it, and the average is maybe 30, 40 minutes. And if you think about a 30-year career, drive back and forth, this is 1 year of your life if you are in that commute. Now, in big cities, of course, there's public transportation, but even in the UK, much of the travel is done by public car. 75% of the people have driver licenses and so on. And if you can give this time back to take your first meeting, take your last meeting, get to the kids earlier, and so on, that's what I'm after, right? So I'd like to give everyone here who drives 1 year back. But there are use cases beyond driving. So basically beyond private driving, right? So many people travel by taxi. So we are looking at robotaxi as well. There is delivery. Our technology carries over. It's not, because it's not programmed, it can learn various use cases. And it can generalize well, not just from country to country, but from use case to use case. Looking further, of course, we'd love to explore more of the physical AI, but this already is quite a bit of work. I'm an engineer, so I'll talk about things that are a bit closer to me. So how does it work? Getting into a bit more detail, in order to, so I said that you need to, in order to apply to many vehicles and to get to large volumes, you need to work with many cars. In order to do that, you need to work with many sensors. Traditionally, sensing has been quite bespoke. You have ISP tuning that you need to pay attention to. If you work with different OEMs, with car manufacturers, they have their preferences about where they source sensors from. You can say, okay, we know how to drive these cars. We will propose a sensor set. But they may say, well, that delays us in our manufacturing process. You should work with what we have. So the good thing about this end-to-end learning is it's less sensitive to very specific aspects in the image, because we're not trying, again, to go for a very specific task about recognizing a very specific object. We're just looking at the driving problem more like a human would. So as a human, I can go and rent a car in a different country. It's a different car. I've never driven it before. It's a different country. I haven't driven there. And I'm able to adapt. So we're going for that, but when you look at, when you go to a different country, the first thing that we do is we go zero shot. And we take a model from the UK, take it to Japan, and let it drive to learn. Of course, this is all supervised with the safety driver and with the safety regulations. But that's, and it learns very fast. Try it again. I think it's back. Can everyone hear me? Yeah. Awesome. We love to be on the road and see how the car does, and to because it learns from data. And this year we started on with the goal to be in 100 cities. Then we raised it to 500 cities. And this is very different from just going from city A to city B. We go, I remember my first time when we opened the office in Germany, I went and I said, I don't want to drive where you've driven. I want to go somewhere else. And when we work with OEMs, they test us by surprising us. They don't tell us which route they're going to take the car on. They just go somewhere. They tell us, be there, and from there on, we'll tell you where to go. This is because we don't have high-definition maps. This industry started with high-definition maps being very precisely located. We gave that up because high-definition maps are hard to maintain. And you never know whether there will be a change after the map was finalized. Maybe it's a lane closure that has to be dealt with. So this allowed us, like I said, 100 cities, 500 cities. At some point, it doesn't matter. You just go to, this becomes a matter of scaling operations. We still learn, we're still in testing, we still learn from all these things, but we have many places where our technology, like from here, we tested to uninterrupted drive from central London to Birmingham, hands off, with a safety driver. And it just went. Just getting to M1 is, for those of you who are local, it's an adventure. It takes, 40 minutes, 45 minutes, and then navigating the highway. And so this was possible only by being there, of course. If you want to, I remember going to Japan in March, and we did not have cars on the road, so we put the first car on the road. But we had to learn locally. There were many interesting learnings about, so you have a model that drives in the UK, and in Japan they drive on the left, like here, and there are lane markings, and you say, oh, should it drive? Well, it should, but stop signs are triangular, right? So if you've never seen a triangular stop sign, then, well, how would the car know? So it has to learn. It can, of course, learn that from data. So we have many data partnerships with OEMs, with other partners, where you learn ahead of the time. So you can train on data, and you can train by imitating a human driver. So basically, I'll explain in a moment how that works. At the core of the technology, there is a foundation model, which serves as it's a world model, basically. Imagine at its core how you saw the world when you were, 5. You already could walk, run around. You understood if you could pick this apple or not. You understand if an object will hurt you or not. You already know geometry inside. Like, nobody taught you geometry, but you understand geometry, you understand kinematics. pretty well. So you need to have this holistic understanding of the world, and that comes not just from driving. It comes from quite a bit of driving, but other tasks as well. So we are feeding this foundation model many, many sources of diverse data. Then the output of this model can also be multiple things. One can be driving, but it can be something else. It can be a next frame prediction. We can ask the model to dream. Say, hey, don't just go there, but tell me what you see when you get there, which actually powers some of our simulation. So, or you can do all kinds of tasks, like classification of scenarios and so on, which powers our data organization, classification, curation. So, but you take this foundation model. Now, the foundation model can be large. It may not fit in a car. And it's not necessarily tuned to drive in a particular location. It's a foundation model that could be used for something other than driving. So then we produce and validate a driving model that, there are 2,000 traffic signs in Europe. So it has to see them. If it never saw them, there's a problem. So we are going through the data curriculum to make sure that our model has seen everything that is relevant. And then you need to deploy. So you need to compress it to 75 watts. And to the sensor set that runs on the car, and make it work with reliability and with the automotive degree of reliability that you expect when you deploy at scale. What does this mean in terms of data organization? This is something, it looks like a complicated picture, but it's something that most everyone in physical AI will go through a flow like this. Basically, you need to collect data from, maybe you get it from someone else's fleet. Maybe you build a fleet. Maybe you just buy data. Then you train on this data. You come up with the model, and then you validate this model. First, you evaluate it in simulation. Then you put it on the road. You have some surprises. And the cycle continues. You can continue with your own fleet. At some point, you need to scale out. Right? Like let's say you build a small fleet for yourself. How large can it be? It cannot be very large. How do you go from there to 1 million cars? There has to be stages of deployment and data collection. This tool chain, what I showed you before is generic. These are some details about our tool chain that make it very powerful. And I'll make this case again in a moment about you need AI to build AI. There is a limit to how much AI you can develop purely with software. And you can see here on the left, basically the car talks. So we trained a language model together with our driving model. So now it's basically one model. And it can explain actions. We actually put in the UK driving code, and it started to reference all the sections in the driving code that apply and why it's slowing down because it's raining, and you need to be 4 seconds behind the vulnerable road user when it's raining. So the second one is what I said earlier about using the model as a generative model. You can do next token prediction as a next frame prediction, and it can go fairly far in the future. So this can generate training data. It can generate test data. Of course, it has to be correct. It has to be useful. It's not just the fact that you generate frames is not enough. There is engineering that has to be applied. And we use models to classify scenarios well. There's a large amount of data that is needed to solve this problem. So how do you know which data? What if you give the model bad data? What if we teach it to drive wrong? So all these problems need to be solved. And large models are able to do very good classifications of scenarios and help us mine the right data and understand which data has to be in. And there is a virtuous cycle here. You build a model that gets better at driving, dreaming, talking about it. And all of this, it educates itself in the future because it selects data better and so on. So speaking of generative models, these are all generated. We force the model, so we can do a few things. We can generate from various types of descriptions. We can, let me try to play that again. Here you see near crashes where we got a bit too close to it. We can take real-life scenarios, and we can resimulate them, but we can go further. Like if the car stopped, we can say, go a little further, don't stop, accelerate a bit more in your dream. This is a bad dream. We're forcing it to have bad dreams. We can force all kinds of bad dreams. It can be bad weather. It can be just maybe crossing over the median, going to the other cars. It can be another car coming towards us. And this teaches the model some things that actually you will not find in data. So you can look for a large amount of data, but there will be limited data that gets out of distribution. So out of the regular distribution, here you have a somewhat exaggerated case where we just let the car go. And this shows you the generative model. It's impressive how much it does, right? This is 10 frames a second, right? So you saw there several seconds. So there are many, you're feeding these frames back to it, so it could degrade, and it doesn't degrade, and it goes in a realistic way. So now you can imagine we can do this at any point in all the data that we collected. We can stop a scene and say, now do this, either parameterize, like go right, so we can condition the ego motion, or do something else, anything that we can imagine. And this can be a randomized search of what could happen, but it can also be an educated search, looking for scenarios, like I said, cross the median in various scenarios and try to put it in situations where it has to recover from. So what does it mean in terms of engineering? First, tame data. It's really data and model. Of course, there is a large amount of software to make it all work, to develop, and so on. But when you deploy a model that fits into a car and is connected to actuation and so on. And because this is end-to-end, from sensors all the way to a trajectory, it's mostly models. But the data is very large, right? This is not text, and the data is not repeatable easily. With simulation, we try to address that. But it's not like with text where you have this text and you have the other text and you're checking that you produce the right text. When you drive on the road, if you drive twice on the same route, you will not see the same things ever. Even if you try to mimic it, it won't be the same thing. So there's a very large amount of data. If you want to collect, I just picked a random number, 1 million hours with a sensor set. If you don't compress, it's an exabyte. This is very large to train on. So you have to be smart about it, but to be smart about it, you have to, like I said, it's a snowball. It's a virtuous cycle. You need to get to the point where you know how to be smart about it, and then you get more data, and you get more smarter about the other data. And you need to understand data. You need to understand computer vision very well. Then, like I said, you need AI to develop AI. We use the models for everything, for simulation, for indexing the data, curating it, figuring out, even for classic robotics tasks like localization and control. For localization, imagine somebody gives you dash cam data. And it's interesting because in dash cam, you may see more near misses or accidents that you would see from a curated data set. But it's only one cam. It's a camera on the dashboard that may be a bit shaky, so the quality may not be good. And then you don't understand the motion of the car and those around you, so you need to build models to actually understand the motion. Of course, you need models for driving. So this is the net result. In the end, all these models are only used offline. When we go to the car, we only deploy one model. That model drives. It does all the driving tasks. It picks a trajectory. It makes sure it's safe. And it generates all kinds of auxiliary signals that are needed for safety or for integration with the car systems. With that, keeping all that in mind, just think about this. These are just pixels. This car that you see here was in Japan. It's a 5-camera system that ran this model. We have several sensor layouts and makeups. That's pretty much all it sees. It just sees all these pixels coming at it, but it makes them into geometry. It makes them into kinematics. It makes them into concepts, higher-level concepts. So concepts emerge. These are not concepts that we program. We don't tell it this is a lane, this is a car. All these concepts emerge, just like they do in language. And the pixels become knowledge and action. And if you do it right, and if you validate it right, that's all there is.